All right, welcome back. So let us consider some examples involving differentiability over an interval. So we want to obtain the derivative of some function, okay, of course, which is going to be in this case in terms of x, such that it applies to any x that lies in the interval. So look at this problem. It says show that the derivative of f of x show that the derivative of f of x equals ln x is f prime of x equals 1 over x for all x in the interval I, where I in this case is equal to or is the set of real numbers such that x is greater than 0, that is positive real numbers. So we want to show that the derivative of this is a function f of x, which takes elements from the set I to produce real numbers, which is defined as ln x. We want to show that the derivative of ln x is 1 over x. Of course, we know that derivative of ln x is 1 over x, but we want to show from the first principle that indeed, following our definition of differentiability that we've given in the previous lessons, then we can establish that indeed this function f of x equals ln x has the derivative f prime of x, which is 1 over x. So now let's go ahead and apply all of those concepts here. So firstly, we identify our function. Our function is defined by f of x equals ln x, or if you like log x to base e, and the domain of this function is defined for when x is greater than 0, okay, as we have it here. So we want to find out what its derivative will be, of course, which will be applicable to this domain. Now let's examine how that works. We say that if we take the ln, if we have the ln of x and we want to take its derivative, then f prime of x should be equal to, by our definition, the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. So basically, this is what we want to do. We want to find out what this limit will be, or in other words, establish that indeed this limit is going to be 1 over x, because in this case, delta x is the variable. It is delta x that is approaching 0, not x. So x will be in our final results anyway. That is, our final result will possibly be a function that depends on x. So how do we go about this? Given that f of x equals ln x, then we know that f of x plus delta x will be ln of x plus delta x. So this is going to be equal to the limit as delta x approaches 0 of ln of x plus delta x, then minus f of x, which is ln of x, divided by delta x. So, and we know that ln is a logarithm. We know that ln is a logarithm, and we know that log a minus log b, of course, provided that they have the same base, say c, is equal to log a over b, okay, to base c. So basically, since we have log x plus delta x minus log x, then we can put them together by this rule to say that this is equal to the limit as delta x approaches 0 of the ln of x plus delta x divided by x, then divided by what we have here, which is still delta x. So we have simplified this expression into this. Now we need to evaluate this limit, and what we know from our knowledge of continuous functions is the fact that since log is a continuous function, we can move it out of this expression so that we take the limit the ln, okay, of whatever this limit is going to be. So this is going to be equal to ln of whatever we're going to get from this expression. That is the limit when we take the limit of what we have inside here. Okay, let's not do that yet. Let's simplify this expression first. We know that we can write this as the limit as delta x approaches 0 of, so for this expression, we know that we can have this as 1 over delta x multiplying ln of x plus delta x all over x. And the reason we are doing that is because we know again that for logarithms, if we have, let's say, b multiplied by log a, okay, to base c, we know this is the same thing as log a to the power of b to base c. So that is the idea we want to apply here. That is, we want to clear this up so that we can bring out this ln. We can bring out the ln that we have here in this case because we still have some other expression here disturbing it, which is this 1 over delta x. So we have put this here so that we can bring it to this power using this rule. So we can say that this expression is going to be equal to the limit as delta x approaches 0 of the ln of, so we're taking the ln of whatever we have left here, which is x plus delta x all over x, then to the power of 1 over delta x. So that is what we have left inside the limits because we have applied this rule to bring this coefficient to the power. Okay, so that's what we have here. And now because we have ln of some argument, we can bring out the ln and then take the limit of what we have inside. So this is basically going to be equal to the ln of the limit as delta x approaches 0 of what we have here, which is x plus delta x. So if I divide by x, that's x plus x divided by x, which is 1, plus delta x divided by x, then to the power of 1 over delta x. So we have all of this, and we'll take the ln of it when we have obtained what this is going to be. Okay, so that simplifies our work considerably. So the problem now at this point is, how do we evaluate these limits? How do we evaluate the limit of this expression as delta x approaches 0? Okay, you may have guessed right, but this is how we go about this. We say that we know that the limit of 1 plus 1 over, sorry, the limit of 1 plus x raised to power 1 over x as x approaches 0 from above, we know it to be equal to 1. Sorry, we know this to be equal to e. Okay, and we said that that was also the same thing with the limit of 1 plus 1 over x raised to the power of x as x approaches infinity. Okay, the two of them are the same. This will also give us e. The only difference being that here x is approaching 0 from above, and here x is approaching infinity, and then we have the other portions reversed too. We have x here, we have 1 over x here, we have 1 over x in the power here, we have x in the power here. So we'll make use of these special limits in simplifying what this limit is meant to be. Okay, but from what we have done so far, this is implying that, don't forget what we equated to this, f prime of x is equal to this. So that means so far we have been able to see that f prime of x is equal to this expression. So the next thing is how to evaluate this expression. So let's see, this is equation star. Well, we try to evaluate this equation star. We'll try to evaluate this limit. Then when we have evaluated the limit, we bring it back to equation star so that we will use that to get our f prime of x. So now let's get started on how to evaluate this limit as it is here. we will firstly observe that in this case, delta x is the variable, delta x is approaching 0. And here we have, instead of inverse of delta x, we actually have delta x in the numerator. And in this case, delta x is approaching 0. So that is similar to something like this, where x is approaching 0. So here delta x is also approaching 0. Okay, forget about the from above and from below first. And in this case, we have delta x right here in the numerator. Yes, this is delta x, this is x, which is a variable over 1. Then we have 1 over delta x here, just like we have 1 over x here. So this is similar to this, but we cannot conclude on what exactly the final expression will be yet. We know it will not be just e, it will be e and carrying some powers. Okay. So for us to proceed with this, we'll find a way to take advantage of this property that we know by rewriting this limit so that it is in this form. And from that, we can deduce that the portion that is having a form similar to this will have its limit to be e. And then once we have that in, we are able to evaluate whatever this limit is going to be. So the first thing we want to do is to attempt to rewrite this expression here, this limit, such a way that it is as close as possible to this expression we have here. And for that to happen, we have x here. Here we have delta x over x. What you should look at is the fact that the variable here is x, so it's like we have the variable. Okay, we have 1 plus the variable. Here, the variable is delta x, and here we have 1 plus the variable all over x. So in this case, because delta x is the one approaching 0, then x will be treated as a constant. Unlike here, because x is the one approaching 0, x is the variable, others can be treated as constants. In this case, delta x is what is approaching 0, delta x is the variable, others can be treated as constants. So from this, we can say that what we have here is indeed 1 plus delta x over x. So if the variable was taken as delta x over x, that would not change the fact that as delta x approaches 0, delta x over x also approaches 0. So we say that to obtain the limit as delta x approaches 0 of 1 plus delta x over x, 1 plus delta x over x to the power of 1 over delta x. We say that what in this case we proceed as follows. We firstly observe that as delta x approaches 0, our delta x over x also approaches 0 since x is a constant. Okay, so if that is the case, then for our delta x approaching 0 here, we can actually replace it with delta x over x approaching 0. Why are we doing that? Because we can see here that instead of x that is common to this, or that is the situation here, we have delta x over x. So we are trying to make a replacement for this there so that we will have delta x over x that we have here. We will also have it at the denominator right here. So that is the point we are driving at now. So let us see how this works out from here. So we will go back to the function. Here we have delta x over x already. So we can leave it like that. It is already 1 plus delta x over x, where delta x over x will be the variable. Okay. So that means that with this, instead of writing limit as delta x approaches 0, I can write limit as delta x over x approaches 0. So that is that about that part. Now the next part is this power. We have this power to be 1 over delta x, but the power we have here is 1 over x. Since our x in this case, that is the variable in this case, will be delta x over x, then we should find a way to make this power here 1 over delta x over x. So we are sure that this is going to be approaching 0 because this is a constant. So if that is the case, we can say that let's use some other variable now. We use some other variable instead of this expression. So let's say let h be equal to delta x over x. So if that is the case, that implies that as delta x approaches 0, we are sure that h also approaches 0. And if that is the case, it means that we can replace delta x by h. That means we want to change the variables completely. We want to change the variable completely from delta x to h. Okay, so we can replace delta x wherever we have it here in this expression by h. So this implies also that from here, if we make delta x the subject, that means delta x is going to be equal to hx by the time we cross multiply this. Okay, delta x will be equal to hx. So we can use that right here. Then we're going to have something like this. It will follow that the limit of 1 plus delta x over x, 1 plus delta x over x to the power of 1 over delta x as delta x approaches 0, as delta x approaches 0 will be equal to the limit. So because we know that as delta x approaches 0, our delta x over s, which we are putting up as h now, also approaches 0. So this expression or this statement is implying this statement. All right. So 1 plus 1 over x, 1 plus delta x over x, that will be 1 plus our delta x over x is now h. So that is 1 plus h. Then raised to the power of 1 over delta x. Don't forget that delta x is hx now by this substitution. So this is going to be 1 over hx. So this is the expression that we have left. We have successfully changed the variable from delta x to h. So if we compare it with these limits, we see that for this case, we have our variable to be x approaching 0. Here we have the variable to be x, and we have 1 over x here. So the only thing different is the fact that we still have x left here. Don't forget that we know for this situation that our x is the constant. Okay, so you can as well see this as something like 1 over 2h, so or 1 over 3h, where 2, 3 in each case in each situation are constant. So x is a constant here. So we can move it out and then just deal with the variable we have left. Okay, so we can say that what we have here is equal to the limit as h approaches 0 of 1 plus h to the power of 1 over h multiplying 1 over x, because 1 over h multiplied by 1 over x will give us 1 over hx that we have here. So we have successfully separated this out. And then we know that since 1 over h, 1 over x is a constant, I mean, since x is a constant, 1 over x is a constant. So we can simplify this by saying that the limit of this expression, okay, everything we have here, we can move out this 1 over x, which is a constant, and take the limit of what we have inside. So this will be equal to the limit as h approaches 0 of 1 plus h to the power of 1 over h, then everything here to the power of 1 over x. So that is the point. Now we have taken the limit of what we have here, okay, because this expression can be written as, okay, let me put an intermediate step here. This expression can be written as the limit as h approaches 0 of 1 plus h to the power of 1 over h, then everything here to the power of 1 over x. I mean, we can move out this 1 over x from here, and just follows from the fact that we know that x to the power of a, okay, all to the power of b. That is when we have this outside, it is just the same thing as having them together being multiplied, x to the power of a times b. So basically, when we have the two powers multiplied, we can separate them out, take the one of them in and put the other outside, affecting all of this expression. So that's what we have done here. And from this, we can now say that this expression here, since this is a constant, is the entire expression here is equivalent to taking the limit of what we have inside first, because indeed this is the only portion that has to do with the variable h that we are working with. And so when we take the limit of that, it will give us these results. It will give us the result that we need, okay, and then whatever results we obtain here, then we raise it to the power of 1 over x, 1 over x being a constant. So To proceed now, we will now see clearly that since the limit of 1 plus x to the power of 1 over x as x approaches 0, yes, from above equals e. Okay, if this limit is going to exist also, it will be equal to e because this is just equivalent to or similar to what we have here. The only difference being the variables. The variable here is x, the variable in the one we have just obtained now is h, and it makes no difference since h is approaching 0. Yes, it is approaching 0 from above. We will see the implication of that. I'll talk about the implication of that as we proceed. However, this is going to give us e. Okay, and that is the limit of what we have right here. Then we have that raised to the power of 1 over x. So what we have here is e to the power of 1 over x. And so that gives us our limits. This is the limit of this expression as delta x approaches 0. We have successfully solved this by making use of these special limits, as you can see, and we did that by changing the variable, so it is easier to visualize how this can be simplified into all of this and why it should be so simplified. Okay, and now that means we have obtained this limit, so we can go back to equation star and substitute the results we just obtained now right here. So we can now say that therefore, okay, in equation star, continuing from equation star, it will follow that f prime of x is equal to, so let's go back to equation star. Equation star says that f prime of x equals the ln of this limit. We have now found this limit to be e to the power of 1 over x. So this will be equal to the ln of e to the power of 1 over x. So with this, we know that we have found an answer. This is going to be f prime of x equals the ln, and we know this is log, so we can move down 1 over x. So this will be 1 over x multiplied by the ln of e, and ln is log to base e, so log e to base e is 1. So to then follow that f prime of x is equal to 1 over x. Now there's that's that about that. That is the result. We have successfully shown that this derivative of f of x, which is which is ln x, is indeed 1 over x, and we have shown that from the first principle as required. Now uh, there's a part where that I asked that we ignore earlier, the fact that we know that the limit here is actually meant to be as h approaches 0 from above. Okay, and that's the reason it is acceptable to just use that here is the fact that the question already provides that we are interested in when x is greater than 0. So what happens when x is greater than 0? That is what we are really after. So that means that we know that this result only applies for values of x that are greater than 0, okay, which is perfectly okay. So this is acceptable, okay, because the problem applies to the situation for which x is greater than 0. Okay, so that is that about that. We have finalized this um, solution to this problem. I've been able to show that the f prime of x is 1 over x. Okay, and we now consider another example. Okay, we now consider another example. So this is our final expression. See that the f prime of x is equal to 1 over x. Now let's consider another example involving derivatives. Let's say that we have to find out. Okay, so we have another problem here. So given in this case that f of x equals x multiplied by the modulus of x, okay, um, we know that in this case f actually takes real numbers and reduces real numbers. Then we have been firstly we want to show that the f prime of 0 is 0. That is the derivative of this function at x equal to 0. That is the derivative exists and it is actually equal to 0. Okay, that's one. And the second thing we want to show, of course, we know this is a piecewise defined function, and 0 will be a breakpoint of it. So that is why we're giving it special attention. That's why this question is requiring us to give it special attention to firstly show that the derivative indeed exists at x equal to 0, and establish that the derivative at x equal to 0 is 0. Now, the derivative, we are also asked to show that um, f prime of x is going to be greater than 0, okay, for all x not equal to 0. Okay, so we want to do two things here. We're given this function, which is x multiplied by modulus of x. Firstly, we want to show that this function has a derivative at x equal to 0, which is 0. And secondly, we want to show that for all other values that is outside 0, that is all non-zero values, f prime of x is going to be positive. Okay, that's what we mean by this expression. So now let's go ahead and do that using everything that we've learned so far. So in this case, we have our f of x to be equal to our function f of x equals x multiplied by the modulus of x. And for the first case, since it has to do with showing that the derivative at a specific point is equal to 0, then it means that we will use this expression having to do with the differentiability at a point, which is the fact that f prime at x naught is given by the limit as x approaches x naught of f of x minus f of x naught divided by x minus x naught, because that just works best when we want to establish pointwise, okay, differentiability. All right, now so um, this is our function as we have written out already, and for this case, our x naught, the point that we want to establish differentiability at, is 0. So that means we should now find out what is f prime of 0. So by making substitution for x naught equal to 0 here, we're going to have this to be the limit as x approaches 0 of f of x minus f of 0 divided by x minus 0. Right. So going back to our function, we know that this is going to be equal to the limit of x multiplied by the modulus of x minus f of 0. That is the value of this function when x is equal to 0. We know that when x is equal to 0, this is going to be 0. And modulus of x, that is modulus of 0, that is still 0. Then divided by x minus 0 as x approaches 0. So basically, this is going to be equal to the limit of x multiplied by the modulus of x divided by x, because this is 0, so ignore that, this is 0, ignore that. So what we have left will be x multiplied by modulus of x divided by x as x approaches 0. So at the end of the day, we can see that this clearly cancels this. So basically what we have here will be the limit as x approaches 0 of the modulus of x. So what is the limit of modulus of x as x approaches 0? We can find out what the limit is, okay, in pieces. So what is the limit of modulus of x as x approaches 0 from above? We have to do it in pieces because obviously this is a piecewise defined function. So as x approaches 0 from above, our modulus of x will be x. So this is the limit of x as x approaches 0. Okay, we have interpreted the from above part, so in deciding what the definition of this would be when x is above 0. So this is going to be equal to 0 when we substitute now. And if we consider the limit of modulus of x as x approaches 0 from below, that will be the limit. When x is approaching 0 from below, the definition of modulus of x will be minus x. So as x approaches 0, and this will be minus of 0, which is equal to 0. So both of them will be equal to 0. So it is evident that, therefore, going back to this expression, since the limit from above equals limit from below, then the limit exists, okay, as x approaches 0, which means that our f prime at 0 is equal to 0. I will just found now. So we can see that therefore f prime of f prime at 0 is equal to 0 as required. Alright, so we're done with the first part of the problem. We have shown that indeed the function has a derivative at x equal to 0 and that derivative is 0. Then looking at the second part of the problem, it says that we should show that the derivative, where's that question again? It says that we should show that f prime of x is greater than 0 for whenever x is not equal to 0. So let's see what is going to be our f prime of x. So for this case, we can use the formula for points, sorry, for differentiability over an interval. So we know that normally that f of x should be equal to the limit of f of x plus delta x, okay, minus f of x divided by delta x. So this is going to be divided by delta x as delta x approaches 0. So for this case, our our f of x is x multiplied by modulus of x. So if we want to get f of x plus delta x, then we know that this is meant to be equal to the limit as delta x approaches 0 of, this will be modulus of, so it is x multiplied by modulus of x. So this will be x plus delta x multiplied by the modulus of x plus delta x, and then minus f of x. F of x is x multiplied by modulus of x, then divided by what we have here, which is delta x. So you want to get the limit of this as delta x approaches 0. So, and firstly, we want to observe that in this case we're interested in what happens as well, I mean when x is not equal to 0. So in this case x is not equal to 0. So if x is not equal to 0, then it can happen that we have our x to either be positive or negative. That means it can be less than 0 or greater than 0. So what happens if x is greater than 0 and what happens if x is less than 0? So let's examine what happens when x is less than 0. We know that if x is not equal to 0, the question says that we should get the characteristic when x is not equal to 0. And if x is not equal to 0, x may be less than 0 and x may be greater than 0. So we consider each of these situations, okay, separately. So we want to firstly find out what happens to this limit when x is less than 0. So when x is less than 0, let's add an additional page here. When x is less than 0, it will follow that our f prime of x, this is f prime of x, please. This is f prime of x. Let me write that properly. This is f prime of x. Our f prime of x will be equal to, so just bear that in mind, it will be equal to the limit as delta x approaches 0 of x plus delta x multiplied by the modulus of x plus delta x. We're not making any simplification to this portion yet. You see why shortly minus. So x, we now know that x is less than 0. So if x is less than 0, modulus of x is minus x. So this is x multiplied by minus x, then divided by delta x. So for this situation, we still have an expression that carries the modular sign. Okay, we have another one that carries the modular sign. And for this situation, we know that this is still a piecewise defined function. Of course, we know this is minus x squared. Alright, so this is still a piecewise defined function. So to clear this off, we can also consider what happens when delta x is approaching 0 from above and when delta x is approaching 0 from below. So we can say that the limit as delta x approaches 0 from below, what is going to happen? Of x plus delta x multiplied by the modulus of x plus delta x, sorry, modulus of x plus delta x minus x squared. So this is minus of x squared, minus of x multiplied by minus of x, that will be plus x squared. And this will be divided by delta x. So the point here is the fact that delta x is approaching 0 from below and x is less than 0. We're considering the case where x is less than 0 and delta x is approaching 0 from below. So if that is the case, that means delta x will be negative, x is also negative. So if that is the case, then the expression we have here will be negative. So if it is negative, that is less than 0, then this modulus will be minus of whatever we have here. So basically, this is going to be equal to the limit as delta x approaches 0 of x plus delta x multiplied by minus, okay, let's write that on the next line so we have enough space to express ourselves. So we have this to be equal to, this will be equal to the limit as delta x approaches 0 of x plus delta x multiplied by minus of x plus delta x. So why? Because we are considering when x is less than 0. When x is less than 0 and delta x is approaching 0 from above, then both of them, both are the two expressions here are negative. And when we have a negative expression here, then the modulus of this will be minus of x plus delta x, then plus x squared. So divided by delta x. So we can now expand this that we have here. This is going to be equal to the limit as delta x approaches 0 of this expression. When we open this up, this is going to be equal to x multiplying x, I mean minus is outside, so x multiplying x, that is x squared, x multiplying delta x, that will be x delta x. So when we multiply it the second time, I mean this is like we're squaring this expression. So multiply the second time, that will be 2 multiplied by x multiplied by delta x, then delta x squared, that will be plus delta x squared, and then we have this thing to be plus x squared, then everything divided by delta x. So when we open up the bracket, this is going to be equal to, I mean this minus is in here, so this is equal to the limit as delta x approaches 0 of, so we know this is minus of x squared, so it will cancel off this plus of x squared, and what we have left by the time we divide by delta x is going to be minus of 2x, because 2x delta x divided by delta x will give us, we have us with 2x left, and this will be plus, sorry, minus, since minus is outside it affects everything here, this will be minus of delta x whole square divided by delta x, that will give us delta x. So this is what we have left, and so when we substitute delta x equals 0 here, this is going to give us minus 2x. So we can see now that having obtained this limit, we have seen the limit from above when delta x is approaching 0. I mean, delta x is approaching 0 from below, okay, and it is equal to minus 2x. So if we try to find out what happens when delta x is approaching 0 from above, what would that give us? So if the x is approaching 0 from above, we still have our x, okay, to be we still have our x to be negative. So basically this expression here will still be negative because delta x is almost 0. Okay, x is less than 0, that is certain, and delta x is as close as possible to 0. So we're going to have this expression here to still be negative, and this limit will still give us the same result. So basically what we have found here is the limit for cases where our x is actually less than 0. So if x is greater than 0, I mean the limit of this expression, if delta x is approaching 0 from below, would not change, and it wouldn't change anything here because we are considering a case where x is less than 0. Since delta x is as close as possible to 0, then this expression here, the modulus of whatever we have here, will still be negative x. Okay, we can also say that this expression here will be it will be giving us the same thing as what we have here, since delta x is approaching 0 and will eventually be crossed to 0 or cancelled out to 0. So the limits when delta x is approaching 0 from above is basically just equal to this. And now we should consider what happens. So we're saying that it also follows that the limit of this function that we are dealing with here, okay, will be equal to, so this one here, limit of this expression, which is x plus delta x multiplied by the modulus of x plus delta x, okay, plus x squared divided by delta x as delta x approaches 0 is basically equal to minus 2x. So whether it is from above or from below, the same analysis applies and the same results will be obtained. And now let's consider what happens when x is greater than 0. So when x is greater than 0, we will have to obtain this limit again. So we will say that we want to find out what's the limit as delta x approaches 0 of, so don't forget where we started or where we got to this point. This is the expression we want to deal with. So we will have this limit to be that of x plus delta x multiplied by the modulus of x plus delta x, okay, minus x multiplied by the modulus of x, then divided by delta x. So here delta x is still approaching 0, but in this case x is positive. So since x is positive, then this is going to be equal to the limit as delta x approaches 0 of x plus delta x remains as it is, x plus delta x. Since x is positive and delta x is approaching 0, this expression here will be positive. So we can just write it as x plus delta x. And this is going to be minus x. Since x is positive, this expression here will just be x. So this is minus x multiplied by x, then divided by delta x. So at the end of the day, this is going to be equal to the limit as delta x approaches 0 of the square of this to give us the same as what we had up there for this portion. This will be plus 2x delta x, then plus delta x all squared, close the bracket, minus x squared, then divided by delta x. So again, this will cancel this, and when we divide through by x by delta x, this is going to be equal to the limit as delta x approaches 0 of 2x, because by the time we divide by delta x, this will cancel this out. So then plus delta x. And when we substitute delta x equals 0 here, this will give us 2x. So we can see clearly that as when x is positive, the derivative is 2x, and when x is negative, the derivative is minus 2x. So it is quite obvious that the for this situation now, don't forget what we have been asked to establish. We have been asked to establish that the derivative when x is not 0 is always positive. So is that so? Let's see what this derivative is now. From what we have obtained, we have seen that therefore the conclusion from what we have done so far is that f prime of x is piecewise defined. It is equal to 2x, it is equal to 2x if x is positive, like we just obtained now. I've seen that f prime of x is equal to 2x if x is greater than 0, and it is equal to 0. I mean, from the first part of the problem, we saw that it was 0 when x is equal to 0. So it will be equal to 0, okay, when x is equal to 0. And we have seen up here also that it will be minus 2x when x is less than 0. So because this is the derivative of the function. The function has a derivative at x equal to 0, like we did establish in problem in the first part of this same problem. Now we have also seen that when x is greater than 0, the derivative is 2x, and when x is less than 0, it is minus 2x. So what can we deduce from this? Can we really reach a conclusion in line with what the second problem requires of us? We have seen that so this means that when x is greater than 0, our f of x is equal to 2x, and 2x will be greater than 0. That is, if x is greater than 0, then definitely 2x is greater than 0. And also we have seen that when x is less than 0, our f of x is equal to minus 2x. We can see that if x is less than 0, minus of 2x will also will be greater than 0. Just like if you have minus 1. If you have x to be minus 1, then minus 2 times minus 1 will be 2, and that will be greater than 0. So therefore, we can conclude that f prime of x, sorry, this is f prime, please, f prime of x, f prime of x. So we can see that in conclusion, f prime of x is always greater than 0, okay, for whenever x is not equal to 0. It is 0 when x equals to 0, and otherwise it is going to be greater than 0. So we have concluded the proof of this, we have concluded the solution to the second part of the problem like this. And just for a check, you can see that this function that is provided for in this problem, this function f of x multiplied by x times modulus of x, we know that it is going to be, if we are to write this out in pieces, this is going to be x multiplied by modulus of x. Modulus of x is x whenever x is greater than or equal to 0, and it will be equal to x multiplied by minus x whenever x is less than 0. So we know that basically the function provided is x squared when x is greater than or equal to 0, and it will be equal to this expression, which is minus of x squared when x is less than 0. So basically, expectedly, when x is greater than 0, the derivative will be 2x. When x is less than 0, the derivative will be minus 2x. And that is basically what we have just obtained here. To be 2x when x is greater than 0, to be minus 2x when x is less than 0. And when x is 0, for us to know if the derivative exists, that is, this is a shortcut to this. For instance, if it was not required for us to show, okay, by working from the first principle, this will be the way we could, or an alternative way to approach the problem. For us to know if the derivative exists at x equals to 0, then we can find the derivative from above, which is going to be 2x multiplied by 2x, 1 substitute 0 into 2x, that will be 0. Check the derivative from below, so to speak, that will be minus 2x minus 2 times 0, that will still be 0. So since they are the same, then we know that the derivative exists at x equal to 0, and it will be 0. So this is like a shortcut or an informal way of establishing that. But of course, if you are going through a situation where it's required for you to show all of this, then we will have to work from first principles like we just did to establish all of this. So that is that about that. Um, this is how it works for derivatives. When it is pointwise, again, we use, or it is more convenient to use this expression. And when it is having to do with over an interval, that is several values of x, then we know it is best to obtain a formula for that situation. However, we can also use this expression over here. That is, the way it is here, we can still use it even when we want to establish over an interval. We can still use the same formula and we'll still get the same result as when we are using this. Because you can remember that we obtained this expression itself from this expression. So they are basically the same thing. Just that in this case, if we decide to use this for an arbitrary point x naught, then it will follow that our result will be in terms of x naught, but then the result will still be the same thing. That means instead of us getting like minus 2x and 2x like we just did here, we would have minus 2x naught and 2x naught. So it will not change anything. The fact will still remain the same thing, and the method would still lead us to the same conclusion. So let us quickly play around with that. For instance, for this second part, let's say that we want to obtain f prime of x naught, and we know we want to use this limit as x approaches x naught of what is that again, f of x minus f of x naught divided by x minus x naught. Then it will follow that for this situation, you would say that this is for this function we have f of x to be equal to f of x is equal to x multiplied by modulus of x, which we can write as x squared as we have broken it down above, when x is greater than or equal to 0, and minus x squared when x is less than 0. That's the function we want to work with. So we know that from here f prime of x naught basically will be equal to the limit as x approaches x naught of f of x. F of x will be x multiplied by modulus of x minus f of x naught. That will be x naught multiplied by the modulus of x naught as x approaches x naught. So at the end of the day, we will have to deal with what is our x approaching. I mean, what is our x positive or negative so that we know what is happening. So for this case, we now consider when x is greater than 0. So when x naught or when x is greater than 0, what is going to happen? When x is greater than 0, this will be the definition that applies. Then we use that definition right here. And we will use the same expression here and then we'll simplify this. So this is going to give us our f prime of x naught will be equal to the limit as x approaches x naught of this will give us x multiplied by x minus x naught multiplied by x naught, because when x is greater than 0 and x is approaching x naught, uh, this is positive, so the modulus of a positive number is x. The modulus of this is also x, so this x naught as indicates me, so this is going to be x minus x naught. And if we go ahead with this will give us the limit as x approaches x naught of this is x squared minus x naught squared divided by x minus x naught. So we know that this is difference of two squares, and from here we can say that this is equal to the limit as x approaches x naught of x squared minus x naught squared. That can be written as x minus x naught into x plus x naught, and this is divided by x minus x naught. So when we do this, we say this, we cancel this, and this will be x plus x naught. When we substitute x equal to x naught, that will be x naught plus x naught, that will be 2x naught. So to give it 2x naught when x naught or x is greater than 0, so as expected, this will be the derivative. But that means that f prime of x will be 2x as expected. So we can do the same thing for when x is less than 0. We will arrive at the same result as what we got above. Okay, so this method is going to essentially give us the same result as this method, just that it's more appropriate and more intuitive to just use this first expression when we are interested in pointwise differentiability. This expression, when we want to establish differentiability for a given point, for a particular and specific point, then this is more appropriate. And if we want to establish it for a set of values in a certain range or in a certain interval, then it is more appropriate to use this expression. So that is that about that. We'll proceed from here in the next lesson. Thank you for watching.